So welcome to this behind the scenes tour of our environment creation suite called CityLayouter. So this is an internal tool that I'm kind of showcasing here. This is the core of all our marketing visuals, and it allows us to create large-scale cities or environments, 3D environments, in a matter of hours. My name is Tobias Frey. I'm a 3D software developer here at vrbn, and I'm just happy to guide you through this little showcase. So I'll like to start this off with a few examples of environments, stuff that has been built in CityLayouter. The first one that we're seeing here is a very dense urban area. It consists of skyscrapers and commercial areas, and it's all in this signature LA style that our current buildings are. But that again is an example of an environment that was created in the CityLayouter. And every 3D asset and texture that you see in the whole presentation, basically, except for cars and trees, that's all from our own library. And many of these assets are also available in our online shop, just as a little side note here. But it's not only like big commercial cities, it's also residential neighborhoods like the ones you're seeing here. And for all those maybe having questions in the whole presentations, in the bottom left, there is numbers for the slides. So if you have questions to a specific slide, it helps to write down the numbers so we might very quickly figure out what the thing is that you would like to have more information on. There's one last that I have as a little intro. It's industrial districts. So you've seen there's quite a range from this commercial skyscraper topology all the way down to industrial districts, and also down to details. If you look at the image here, there's quite a lot of stuff going on here, and this is very important to us. We want to have the CityLayouter as a tool to generate cities that are kind of give a very complex feeling. And for this shot, for example, there have only been a few manual adjustments needed to really create the scene that you're seeing here. So what I'm going to guide you through is a presentation in 3 parts, basically. The first part is going to be from a distance. It's going to be the ideas behind the CityLayouter, the basic workflow that we have. So it's kind of a light introduction to the whole thing. The second part is going to be what I call the brief city stroll. It's the idea that we just have a look at this tool, look at some of the features that are implemented. Of course, we can't look at all of them, but I picked out a few ones that I thought would be interesting to look at. So that should be kind of a source of inspiration for your own work. And the last bit, called the urban fabric, the thing that keeps it all together, this is where we're going to go really down to the technical details, because I think it's a CityEngine user meeting, and I'm also happy to share like very technical stuff with you. So maybe for those people more interested in the general thing, chapters 1 and 2 will be for you. Chapter 3 is going to be more for the really tech-savvy people. But I'm super happy to share a few best practices from our side here. But let's kick off the first bit from a distance. So what is the core requirement for the CityLayouter? Well, it needs to create believable cities that should be dense, that should be detail packed. They should be art directable. We don't want to have a tool that automatically generates huge cities, but we can't control how they look. So it should really have this chance of like changing things and making them in a way that in a look that you want from it. So should be art directable. And the last bit, it should allow rapid iterations. So all the exports, it's all fully automated. And if we see in one of the final renderings, oh, there's something we want to change, it shouldn't take weeks to go back to this thing. It should be a matter of minutes to fix it. So especially with like this creative process, it very often needs to go in a few cycles. So having these chance of rapid iterations is really a core requirement for the whole tool. How does the CityLayouter kind of work on a very broad level? Well, you create a city in CityEngine with the tools of the CityLayouter. We have this custom export that exports to a very simple format. I'll come back to that just in a minute. And then we visualize things. We visualize them, for example, in Unreal Engine. All the stuff you'll see in this presentation has been made in Unreal Engine, but due to the nature of our exporter that is very generic, we can also go to other destinations. We can go to Houdini Redshift, for example. We can go to Blender. Any other game engine or renderer is potentially can import that information and use it, because our export is very basic. It consists of unique geometries, for example, stuff in the landscape that is just very unique that can't be instantiated. And these are basic OBJ files, so just 3D data. And then we have a lot of information that is just reported location of instanced objects. So where a building is, it's just a point location, and information which building with which rotation, which size, and so on. And this makes it very generic and super helpful to just switch in between output tools where we want to visualize it. But you might ask yourself now, yeah, why Unreal? Well, I think the easiest point to make why Unreal is just showing you these 3 renders. So this is the first one, there's a second one, and we've got a third one as well. And there just lies a few minutes in between these. And I think this is the really big advantage for us, because as I said, it's for creating marketing visuals. So we want to have that stuff quickly, and we need to tell stories. And if we can just change in between those moods in a matter of seconds or minutes, it's yeah, big advantage for us. What is the output of the CityLayouter? So on a CityEngine side, well, it's what we all know from if we have designed street grids in CityEngine. So what you see here is quite a big example of an environment with 8 kilometers or 5 miles in diameter. On the left, you kind of see like this graph look, and on the right, you already see the applied rules that generate the forest, that place the buildings, that create the ponds, those water areas, the streets, and so on. Maybe a few fun facts about that environment. It consists of a bit more than 7,000 buildings, and the road network has something of 240 kilometers of roads, so roughly 150 miles. And I think what's really a fun fact now, it consists of more than 124,000 pallets. We'll talk about pallets later, but yeah, keep that in mind. It's a pretty big one. If you look at it from the side, just another impression of that same environment. You also see it's not perfect, but as I said, it's for marketing material. It doesn't need to be perfect to the last bit. It just needs to be believable. And as soon as I'll show you the next picture, I'm pretty sure you will consent with me that it is quite realistic. So this is what we use that environment actually for. It was a real-time showcase, just visualizing a helicopter flight through that environment in real time. And it was mainly there to demonstrate the capabilities of our buildings, especially the parallax occlusion feature of the interiors. If you want to have a look at that video, just search in YouTube for helicopter demo urban written vrbn, and I'm pretty sure you'll just find that video, have a look at it. And with this, I would like to finish this first bit, so that should have given you a very brief introduction to the CityLayouters. And now let's head into the second part and check out a few of its features. So we're here for the brief city stroll. As I said, we could look at features for hours, but I just tried to demonstrate a few of its features. So some clever CGI rules, and some of the stuff is also in combination with Python scripts. So the idea, as I said, is to inspire you for your own CityEngine projects. So just let's start with one of our urban topologies, one especially like highlighted on one of the renderings you've already seen. So that one here that I kicked this presentation off. It's about commercial lots. So we have our kind of understanding of what commercial lots are inside the CityLayouter. It's a very dense urban typology. So it should also incorporate some free spaces, some parking areas, a bit of green spaces, and most of the buildings should be kind of oriented towards the streets. So in this building here, you'll see 2 examples just kind of highlighted, where basically that whole block is the input for the rule, and the rule then comes up with a solution that kind of fills the space as good as possible, places buildings according to a few settings that our artists can control. And this is exactly what I would like to look at in the next few slides. So the default setting is a very high building density. The building maximum height is at -1. This is very often used as a default value, or in our case here as an invalid value. So as soon as it's above 0, it will actually be a filter. And we have a control for the vegetation density. There's so much more controlled through these 3 attributes, but as I said, we want to have it art directable, but it should still be not too big, because if you look at an 8-kilometer diameter city, you can't go into every single lot and control all these things. So we want to have like very broad controls that still make it art directable, but not to like the smallest detail. So we could now, for example, reduce the building density and increase the vegetation density, which would give us an image like this. I'll jump back and forth a bit to give you an idea of like what changes. Or we could go further and say, yeah, it's maybe like this very suburban area. We don't want to have like too high buildings. So we can just add this building max height slider to 25 meters, and all the buildings are going to be a maximum of 25 meters high. Or we can play around with it and make it, okay, 30 meters. And this just gives us different results. And of course, by changing the random seed, we will get other solutions again. And this is a very quick way for us to really create these dense commercial lots. And I think that's a very important takeaway, and it took me some while to learn that. If you do debugging in CityEngine, don't rely solely on print statements or the hierarchical visualization of the tree. Just go full Sims mode. Add stuff in color, add these little cubes with colors that tell you, for example, which is like the main street front, which is yellow in that case. Where do you feel like a lot is kind of ending? These are the red cubes, and this helped me a lot with like writing this code. So really use the visual capabilities, and just as kind of a little tip on like how I try to develop these things. What you see, the areas in the colored areas in like yellow and blue and stuff, this is all kind of offsets that I used, and I very often visualize these things to make sure that the code I'm writing in CGA is really doing what I want it to do. And let's just finish up this first bit on commercial lots with 2 Unreal visualizations of such environments. And then there's a second one, especially in the front left corner, you'll see some of these commercial lots with the quite densely packed together buildings. But you also see another feature that is kind of brand new. It's overpasses and bridges. It's kind of a beta mode. Not everything is perfect yet, but I'm super happy that we're at this point where I'm kind of think it makes sense to look at it, although it's still a very early preview. So these overpasses, they build on the street graphs. So that means you have a fully integrated graph network in the whole environment. Later on, that could be very helpful if you want to have cars driving around and stuff like that. So another view is that one here. So you also have like these freeway intersections. And you might see that the piers or the pillars here, they aren't spaced equally. That's for a reason, because if we look at the next one, we'll see that we have occlusion queries that react to the stuff that is built below the bridges. So the bridge rule really avoids the buildings below and just builds piers where there's nothing built below. And this really helps with a believable city again, because it is kind of dense. There isn't like huge empty areas. And it also kind of architecturally makes sense. And just changing a few settings on those bridges, you can also go to a look that looks like this. I'll jump back and forth. For example, look at the guardrails or the under construction with the piers, with these cap beams. There's quite a few things changing. And yeah, there's just another shot like below these bridges, how it looks. And of course, here again, it's interesting to look at this whole thing, how it looks in Unreal if it's rendered out. And we'll get things out like this. And I've just few more impressions with me, because I think it just makes sense to look at it in like the final visualization, because what you see in CityEngine is a very simplified version of it. Here again, you see that bridge on the right. It's this very small environment where we took all these renderings just for this demonstration here. It was the environment, I think I built it in 1.5 hours. So maybe to give you a bit of an idea how quickly these things are built with the proper rules at hand. That's another one like towards the evening. And then we've just this very last shot here. As mentioned earlier, it's important to us to have this CityLayouter as a tool to build believable cities. And that also means that they have a lot of detail. And now we're coming back to what I said before, to the palettes. You'll see these stacks of palettes standing around. These weren't placed by an artist. That's also distributed by our code. Same goes for the concrete tubes on the right. And this brings us to the third and kind of last topic of our brief city stroll. And it's these assets that bring our environments to life. One of these assets, as I said before, is the palettes, but the thing is just distributing these randomly with like a point scatter. It doesn't really tell a story. It's gonna look super boring, way too random for it to really exist that way. So they very often exist in coexistence with other assets. For example, a stack of these. And this is where our concept of assemblies comes in, because this really helped us with moving on to the next step of like realistic visualizations. And so I'm going to talk about assemblies and not assets. Maybe just one thing to say here, I'm demonstrating these on our own assets, but for sure that workflow that I'm describing now would work with any other 3D asset, because it is just a 3D asset and it can be exchanged for another one. As I said, it helps with telling a story because you can see there's people involved in that environment. So these assemblies, first idea, okay, we can write CGI code, randomly rotate things. But the thing is, it's just the diversity you get from manually placing them is so much bigger, so that we opted for assemblies that are manually built. For all these assemblies took one of our artists maybe 40 minutes to build, maybe half an hour, not more than that. But they are like super interesting in how they look, like stuff at an angle. Some things here are even not possible with CGI. It would take you forever to find solution to really make it look realistic. So we have these assemblies that are manually built, and that takes a bit of time, that is right. But if you use these then to place them in the city, we just get so much more life out of it. And the important thing here that we needed to solve is to make it as easy to render or visualize in a game engine as possible. We want to instantiate as much as possible. What you see here, it's just 3 different assets. So in 3 different color variation of the same palette. So we don't want to save each of these assemblies as a new 3D geometry, because this would just add a lot more geometries, so more things that needs to be instantiated. What we want to have here is just instances of the same 3 assets. And how we did that is what I'm going to show you on the next slide, because I think it's a very interesting concept for this problem. So in the first step, we built these assemblies. So that means we place the 3D assets through a rule that is important for later on, because that rule needs to report stuff. We could also build them by CGI, but mostly we built them manually, as I said. We would then have a Python script that runs this assembly manager, how we call it, and it does load from an existing CGI file, a rule file, information on already existing assemblies. And you might already get an idea of where this is going. We then select that assembly that we want to save, and we run a script that imports that assembly. So the selected shapes with each of their asset that it inserts. Each of these shapes reports the location of the asset and its orientation and size and so on. And that information is gathered by the Python script and written back into the assembly CGI rule file. So the interesting thing, what we're doing here, we're having a Python script that writes CGI code, and it allows us to create these assemblies, but just save them as the location of assets relative to a new 0 point. So we just take all of them, we calculate what is the bottom point in the middle, and then we have the relative distances from that bottom point for each and every asset. And this allows us to easily create new assemblies and then place them in our environments, and without having to store more and more new 3D objects, we just save their location and orientation. I hope that wasn't too fast. I'm super happy that we have a recording, so you can go back and look at it again. But I think it's just an interesting way of dealing with this problem and combining Python and CGA in CityEngine. And as an example for this shot here that we've seen before, you can spot there's quite a few areas where we've placed these assemblies and that really bring this whole shot to life. We've got another one directly from CityEngine where you can see other assemblies. But you might tell yourself, well, we've just looked at assemblies like one stack, but what you're seeing here is kind of combinations of different assemblies. So they have kind of patterns. And this is something I would like to look at in the next and last part of this presentation. So coming to the urban fabric. Yeah, get ready for quite a bit of code now, but I hope you enjoy it because it's interesting details and I'm pretty sure you can take stuff for yourself and learn from it. So let's go. So as I said, these are kind of patterns of assemblies. So we've got a pattern here that is the usage of the pattern is industrial. It has a probability of 20% to be built. It consists of different patterns. We would say maybe sorted and loosely. These can be any name, but I went for these, for example. They have certain assemblies in it. So the pallet stack 001, this has kind of a few variants in it. And it has a density of 85%. And we've got this information for all of these patterns. I'm just highlighting 3. And for example, with the green one, that one has also a probability of 20% to be used. It consists 50% out of arrays and 50% out of rows. You can see here it's built in rows, or at least a pattern that I call rows. It has a density of 90%, so roughly every 10th pallet is missing. And it consists of the assemblies pallet stack 001 as well as pallet stack 002. And you can, of course, make up every combination of assemblies and patterns and their densities and probabilities. But if you think about that information, well, how do you bring that into a CGA rule? Because it's quite a lot of case statements. So the basic way of doing this, or the standard way of doing this, is, well, you have a lot of case statements. You go for the first case, that is the usage, it's industrial, okay. And then for the green one, it's this 20% chance that it goes into that 50-50 selection again. And you can already see this gets to a very, very long list, and it's super hard to maintain. And you also have a lot of redundant code later on because the assembly rows for A might look different than from B because it's had different assemblies in it and all that stuff. So maybe it would make sense to have a bit more complex data types in CGA that you can kind of save data in and do stuff with it. And this is what this first part here is about. It's about how can we manage more complex data than maybe just an array of float values or an array of strings. And the solution we came up here and that we're really happy with because it's really easy to maintain is the following. So we have this pattern lookup table, we call it, and it still has some case statements in it, but it's way more reduced and it saves so much more information in it. And especially it's very easy to maintain for us. So again, the same pattern, the green one is this second row. It has a 20% chance, so the first entry is a 20% chance to be used, so the probability of usage. It has a name, we call it pattern B. Then it has information on the different patterns it can have, 50-50 in between array and rows. It has information on the density, and the last entry is the assemblies that are being used. So we can, on one line, have all the information we need for these patterns, which is great. But how do we access that information? Well, we first select one of these rows and we say now, okay, it's going to be pattern B. This is what happens in the get assembly group. The idea here is the same as in the get pattern. So I'm just going to look at the get pattern version. And we're just going to feed that get pattern function the information out of which patterns we have. So like the third entry in that assembly group. And that looks something like that. I try to hide some stuff away, so that's why get pattern exists twice, and it just adds some information. I'll feed it in this pattern array on the top right, which was created on the last slide. And once again, the recording might be really helpful to go back and forth in between, because I'm aware that this is quite complex what we're looking at here. And this function has a stop criteria. It's going to be a recursive function. I can already tell you that. So make sure you always have a proper stop criteria, because otherwise you might run into infinite loops. And here it's a very simple one. As soon as the counter reaches the size of the pattern array, so in that case, it is a pattern array with 2 entries, and the counter reaches 2, it just stops and returns invalid pattern. But we hope that never happens, because we try to select the pattern by percentage. So we just read out at the location of the counter, and in the beginning that is 0, the value in front of that line, and that's 0.5. And we divide it through 1 minus the sum of all percentages that have already been used. So that's actually still 0. So it's 0.5 divided by 1, that's 0.5, so 50% chance of it happening. If that is the case, we return the information on the pattern we're using, so that would be array. If that isn't the case, well, we move on inside that array, we just increase the counter by 1, and the sum for P is the one we just used, so 50%. So the next time we're visiting this with the counter at 1, it's going to pick 0.5 rows, and it's going to divide 0.5 by 0.5, so it will for sure pick rows. And with this P sum that is summed up, I make sure that I still have like equal chance of selecting them exactly by what I wrote down. Because if I would not do that, I would, for the second one, only pick 50% of the results, and that would just be wrong. I want to have all of them, because the other 50% weren't picked in the first run. I hope that makes kind of sense. Otherwise, go back, watch it a bit slower, and I'm pretty sure you'll get the hang of it. But it's a cool way of saving complex data. And it allows us to create environments like that one here, with all these assemblies standing around in ways that kind of make sense, because humans could have placed them there. And then there's one last bit that I would like to show you. It goes into a bit different direction. It has to do with these residential buildings. Once again, a rendering we've seen before, and you might have wondered, it's quite densely packed, but there's like, it makes all sense. It looks really good. Well, it doesn't if you run it the first time, that code. And so this part is about optimizing CGI results. So we've got a block here with different lots on it. And I may ask you now, what is the problem with these lots? And I'm pretty sure you'll be like, yeah, well, I don't know. It's the same for me. I don't know what is different with them. But if I generate the code that creates our residential buildings, well, these lots will be empty, for various reasons. Very often it's just a random value picked slightly too big, slightly too large, so it just can't fit the building in there that I wanted to fit in there first time. So what we do here, instead of making sure that it really fits very early on in the rule, we kind of brute force a solution. So we're just generating several solutions for the same lot, and then have a Python script selecting one of them that actually works, setting the start seed to a seed that actually worked, and we have solved that problem. I did prepare a slide to run you through the logic within CGI code. I'm running slightly late, so I'll rush a bit through, but as I said, there's a recording. You can look at it in your own speed after we're through here. So there's a Python setup, a script that runs the CGI code on all of these lots. And the CGI code then creates and reports solutions. So only if it's a solution where really a building could be built, it reports the CDN of that solution. The Python file then collects these reports and selects a winner and sets the CGI attributes on these shapes. And the CGI then recreates the selected seed. to run you through the code. I tried to make it as simple as possible. I hope it's easy to follow along. So we've got a start rule that is named looking for best fit. The find best fit mode is a Boolean that is activated. That's what the Python setup does, because we want to find the best fit. So we go for the try seeds. We have a number of tries. In this case, it's 20 tries. So we try the first seed. N is 20, so we're going on. We set a current test seed. We build the lot, start doing things in building that lot. And at the same time, we just try again with seed number 19, 18, 17, and so on until we reach 0. In that build lot, we'll do a geometry check, see if the shape is suitable. Yes, it is suitable, very good. And if it's in the find best fit mode, which is the case, we set that Boolean to true, it will report the winners. And reporting the winners is pretty easy. It just reports the CDN value and the current test seed. So with that information at hand, the Python script can collect it and then later on set that seed. And as soon as we're not in the find best fit mode again, so we will be at line 22. If there is a chosen seed, we will set that seed and we will build the lot and in the end insert the building and have a proper solution that works. I hope that is helpful for you. It's very helpful for us at least. And I think it's a really nice way of how you can optimize your CGA results. And with that, very techy ending of the presentation, I have something, again, more beautiful to show to you, and maybe as an inspiration of what CityEngine is capable of doing. And here as an example, what our CityLayouter is capable of doing. And with this, I'd like to finish my presentation and like to thank you for your attention. Thank you very much.
All right. Very cool. Sweet. Thank you so much for the presentation. Let's do a couple of questions, if there are some questions. I saw one before from Nikolai. Toby, do you see the I'm going to ask you the questions. I would assume you know the answers. Otherwise, I'll jump in. All right. So Nikolai was asking before, do you use PBR textures in CityEngine and export them to Unreal, or do you basically map the stuff only afterwards in Unreal, or do PBR materials only exist in Unreal?
It's the second. They only exist in Unreal, just to keep CityEngine as light as possible. And in if you're in this design phase, it just makes sense to have this certain level of abstraction, and it's kind of appreciated by the artists. So we just keep it as simple as possible, although we could already go further there.
Yeah, maybe just to ask there. So it's as you have seen from Toby's presentation, we're basically developing the workflow tool agnostic in the sense of where we can export to. So our entire library that we have with all the buildings and all the assets and all of the materials in general, they are fully, or the entire library is fully PBR. So it's not kind of just PBR in Unreal, but even if we export also to other tools, there it's also fully PBR because the entire library is fully PBR in general. But then also to work efficiently and fluidly within CityEngine, what we're also doing is we're using a lot of proxy geometries that are super simplified, that just represent the object kind of visually. And then also in CityEngine, we don't need the full resolution of all of the textures. So we have automation scripts that basically take the entire library and create preview textures that are very lightweight, so we still have an impression of the stuff in CityEngine, but we don't need to fully load everything from the server. All right, a question from Bryant. Was this a close track?
I'm pretty sure it doesn't look like a close track.
It's actually super fun because the red Toyota car is actually one of our co-workers actually has one of those red cars. So we basically said, hey, let's use that one because it's a super cool car. Sweet. Are there some more questions? I don't see one right at the moment. Yeah, no questions at the moment. Thank you, Toby, for the presentation. Much appreciated.